The following program is brought to you by Caltech.
I'd like to go ahead and introduce our panelists. So we have three faculty investigators from the LMI EFRC here that are going to be joining us for a panel discussion on future directions for light material interactions in photovoltaics. So we hope that our online audience will also participate by asking questions or making comments during the in the chat portion there, and Bryce here in the audience will ask those for you. So we have our three panelists. On the far left, we have Professor Nate Lewis. He's a professor of chemistry at the California Institute of Technology since 1991. Since 2010, he served as principal investigator of the Joint Center for Artificial Photosynthesis, the DOE's Energy Innovation Hub in Fuels from Sunlight. And since 1992, as the PI of the Beckman Institute Molecular Materials Research Center. His research interests include artificial photosynthesis and electronic noses. Professor Lewis continues to study ways to harness sunlight and generate chemical fuel by splitting water to generate hydrogen. He's developing the electronic nose, which consists of chemically sensitive conducting polymer film capable of detecting and quantifying a broad variety of analytes. We also have in the middle here Professor Paul Alivisatos. He serves as the 7th director of Lawrence Berkeley National Laboratory, succeeding Stephen Chu when he was sworn in to the U.S. Secretary of Energy position. Professor Alivisatos has led a distinguished career in chemistry and nanoscience research. He's made groundbreaking contributions to the fundamental physical chemistry of nanocrystals, including the synthesis of size and shape-controlled nanocrystals and studies of the optical, electrical, structural, and thermodynamic properties. He has demonstrated key applications of nanocrystals in biological imaging and renewable energy. He's currently the Larry and Diane Bach Professor of Nanotechnology and is a professor in the departments of Material Science and Chemistry at UC Berkeley. And closest to me here, we have Professor Paul Braun from the University of Illinois at Urbana-Champaign. He's the Ivan Racha Professor of Material Science and Engineering and an affiliate of the Frederick Seitz Materials Research Laboratory, the Beckman Institute for Advanced Science and Technology, and the Department of Chemistry, the Micro Nanotechnology Laboratory, and the Mechanical Science and Engineering departments. His research focuses on the synthesis and properties of 3D architectures with a focus on materials with unique optical, electrochemical, thermo, and mechanical properties. So we welcome any questions. Although the focus of the panel discussion is going to be on light material interactions, we're open to many topics. So I think we had one question that was submitted early that I think would be a great one to start us off. So Bryce, if you want to ask that one for us.
So due to the need to implement solar technologies on a massive terawatt scale, currently we have several competing technologies from traditional silicon PV to solar thermal, and then emerging technologies that use either organic or semiconductor nanocrystal components. Do you think that in the end we'll utilize a combination of these techniques, or is there going to be one predominant winner among these possible technologies? So maybe you don't have to pick the winner, but just whether you think it's going to be one or a combination of many.
Who wants to take that?
Well, that's a hard question. I think what's remarkable, and I think Harry and Eli touched on it in their talks, maybe John to some degree too, that we're in this period where I think 5 years ago, the feeling was that this area was quite wide open in the sense that it was still the case that the silicon technology was still quite expensive. And there's been this remarkable development of the drop in the price there, and it looks like it's still heading down. And so that's changing a lot of the thinking. And I think what the earlier speakers showed is that to the extent that there will be room for new things, it has to be both high efficiency and low cost. And we've had, I think it poses a bit of a challenge to the research community because research does take quite a bit of time. A lot of people set off 5, 6, 7 years ago to work on new ideas related to solar that were associated with technologies where they felt like they could easily scale to high volumes, but would potentially not have very high efficiencies. And I think that most of those things have basically, I don't want to say they've been wiped out, but their reasoning underlying them has been shaken a bit. And so one has to pause and think about that. And it becomes a question now of whether, for example, let's take you mentioned organic solar cells or quantum dot-based solar cells. I think it's actually important, even in this period, to continue work in those areas because it's open-ended how far one can get, for example, with electrical transport in an organic system. What are the true limits to that are not really established and so on. But I think the kind of rationale behind it today would probably look quite different than it would a few years ago. And as to your ultimate question of will there be a final system, well, I would take away from this morning's talks that silicon is reigning supreme, and the question is, will one of these other clever combinations displace it by having both high efficiency and low cost? Quite possible. It looked very encouraging what I saw. So.
I guess I would add to that. I think that also you have to think about there's systems which are large area solar tracking based systems where the sort of front-end solar management is very different from something that may be stationary and roof-mounted. And so for the systems where we have solar tracking, we're already seeing that it's really the balance of systems that matters because at these high concentrations, the module cost is a very small part of it. On the other hand, if you have systems that are not tracking, now really it's the absorber cost becomes very relevant and very, very careful photon management so that you lose as little of the photons on the front end are really critical. So I think in those two spaces, we may end up seeing that there's a specific subset of technologies that works in the tracked systems, and then a very different subset of systems that work in stationary, for example, rooftop systems. And you really have to look at the full balance of systems because the balance of systems cost in those two is drastically different, and the effective module cost versus the effect of all of the front-end solar down to the cost of the steel to mount the package.
Follow to that. What efficiencies then would you expect to be shooting for in terms of something that would be a large tracking type of system versus something you would want to put on a rooftop? What efficiencies are ultimately going to be good enough?
What do you think, Nate?
I think there are two completely opposing views on this at both ends of the spectrum. We're buzzing. Well, not me. Someone's buzzing. One end of the spectrum is that to first order, to be the contrarian, since there's not enough money in all the governments of the world to continue to subsidize solar until it becomes a significant part of energy, which it's not now, that all the companies are going to go out of business. There won't be a single one in 10 years that would survive because because there's no such thing as grid parity, because it's not baseload power, and it would just be peak shaving, and it'll be by definition a tiny fraction of energy, and therefore it's open, clean slated. That any improvement we can make, and we should think about significant improvements in efficiency and in the way we make cells and modules and balance of systems, because you don't have to worry about competing with existing technology because it's destined to be doomed. This is one view shared by many people, not necessarily in this room, but shared by many people. So forget about silicon, and don't have to worry about beating the cost because it's doomed, even as it gets cheaper and cheaper. The other view, of course, is that silicon was, and always will be the basis of PV technology for a very long time. And if you can't beat it on cost per watt, then you're not in the game. I have no personal opinion on which of those two contrary views or some nonlinear coefficient in between is the right answer, but they both have merit. If you go to the latter one, then I think it's pretty clear you should be talking a 40 or 50% efficiency. It's hard work, and you see it's beautiful, but it's hard work to think about 1% improvement in efficiency here and there on the margins. That's important, it's good to do, but there must be fully disruptive concepts that think about doing this in fundamentally new ways, that instead of go to 1% or 2% upon existing technology with very sophisticated index changes or angle reflection coating, that shoot to 50%. And there are, in fact, some designs, intermediate gap cells and other things, light managed cells, integrated structures. And I think that we should actually be doing that, because if you can fundamentally change disruptively the cost performance equation, then you can obviate both of those ends of the spectrum at the same time.
Any other comments from our panel?
So why did you say that you don't think it's possible to achieve grid parity? That's a critical piece in your statement there. I agree with what you said about wanting to have, to really try to think about things that are very new and trying to go for the higher efficiencies. I totally agree with that. But I mean, the numbers are the numbers. I looked them up a few weeks ago, and it was actually, you could buy modules on the international market at 60 cents a watt or something. The number is still going down. Sure. At some point in there, it does achieve grid parity. I don't quite understand why you say it doesn't. In many markets, it has already, and the markets are growing at a very large pace right now. So just explain that to me. I didn't quite get it.
So there are two different definitions of grid parity. There are the ones commonly used in the intermittent renewable energy community, that on the levelized cost of electricity, that you do what it would cost to generate something by another method, for instance, from coal, a nickel a kilowatt hour, whatever your favorite number is. And you levelize cost of that against solar, but it is fundamentally an intermittent resource, and it is not the same thing. Grid parity is not the same thing for even a levelized cost of electricity made from an intermittent source as from one that can meet demand whenever and wherever demand is. And you can only go so far with demand management, because on a cloudy day, when the wind don't blow, you cannot have a big red switch that says United States of America on it. Sure, that's flipped, okay? So I think there is no such thing as grid parity.
So
it's not a valid concept. It doesn't mean that cost reductions won't capture increased market share, but it does mean that there's going to be a ceiling onto the amount of energy that we will ever make from an intermittent resource unless we compensate for the intermittency in a robust, reliable way.
A ceiling for sure, but
right.
I mean, so you're saying that the German experiment, for example, is just doomed to failure. I mean, they're getting, 15% of electricity throughout half the year from solar. That's a very big fraction of their grid. They're actually really happening there. That's a substantial energy. I mean, I don't think there's going to be any one source of energy that's going to be the final answer. So if you get up into the 10-15% range, that's a very substantial impact. Right. Okay.
That's right.
All right.
Okay, do we have a question from online, or? Yeah.
So Professor Braun talked about how we have these two very different designs for centralized system versus solar cell on your rooftop, and then given Professor Lewis's comments on the fact that solar is inherently intermittent, one of the questions online is, would you envision having a solar cell on every rooftop, or do you think that the trend is going to go towards these large centralized systems, given that we could find a way to meet the flux and demand?
I mean, I think one thing to keep very much in mind is also the distribution system. Now that, of course, is not our focus here, but in certain regions where highly concentrated, centralized systems work well, they tend to be displaced from population centers. And so the net cost or net value of electricity produced in Arizona is different than that produced in Massachusetts. But the kind of system that you would install would also be radically different. And I think from a personal standpoint, that's really where thinking about sort of light matter interactions and light harvesting approaches, because how you're going to work with a photon that you get in one environment is drastically different than the other. So there is not one answer. It really is a regional problem, and the German experiment is a regional problem also, because they have 6 months of the year they have a pretty good light source, and 6 months of the year they have a horrendous light source. And so they have to be able to deal with that and have a grid and a nationally integrated power system that can handle that.
So back to, I guess, some of the expertise in our center. Professor Braun's group makes these beautiful 3D architectured photonic crystal structures. Oliver Santos' group is making all these nanocrystals. Nate Lewis's group with the microwires. How do you see some of these aspects of nanotechnology or complex optical geometries being integrated with photovoltaic devices in a way that'll help us achieve high efficiency, but not an expensive, really high cost? Or does that really matter? If you get higher efficiency, is it worth the cost?
For us specifically, I mean, in the nanocrystal quantum dot business, we pay very close attention to whatever Eli says, and so listening carefully, we understand that you want to have a material that has a very high quantum yield, and it turns out we can make nanocrystals with very high quantum yields. And so most of the work that has gone on with quantum dots and solar cells has actually not had, the individual components have not actually had high quantum yields, because they hadn't really done enough to build the architecture of the quantum dot in its complete way. So we're looking, for example, when Eli says, okay, we need a 2.1 or 2.2 EV gap, it's very easy for us to tune our gaps around. Or when people say, well, we want to have the ability to split into 7 or 8 colors, that's very challenging to do with semiconductor materials that have to all be epitaxially integrated with each other, but actually not so difficult to do potentially with quantum dots. So in our case, the focus is on how can we electrically extract charges from a system that has a very high quantum yield when it's not contacted in a quantum dot kind of system. And that's where we're focusing our efforts, trying to learn how to make contacts to systems that will have the very high quantum yields.
What about the photonic crystals, for example?
You know, I think really our viewpoint on that is that photons are very valuable, and we need to think of approaches that can take white light photons and use their maximal energy with minimal thermalization. And so rather than worrying intrinsically at, say, the cost at the front end, what are the fundamental limits on how effectively we can take photons, distribute them potentially according to their energies, harvest them according to their energies, and these complicated or relatively complicated photonic architectures are sort of the one limit of being able to do that. And I think what we'll find is that maybe we'll get 98% of that value with a much simpler structure, but knowing that fundamental upper bound is very important.
So my view on this is, again, kind of 30,000 foot level view. I think that the real opportunity here is to merge these disparate functions which are being put together in a two-dimensional plane from separate functionality. We heard about glass for spectral splitting, and then discrete light absorbers with discrete band gaps in a two-dimensional plane. And the glass was a two-dimensional plane. And then we heard you couldn't use a prism because we didn't have enough ways to fit it. And on like this. I think that ultimately we're going to have a set of photonic or optical or metamaterials that's a graded index material that acts as the prism, that spatially, internally in that prism, in the volume, is going to have a spectrally split set of different bandgap solar cells. It's going to be one material that's going to be made one way, one time, and it's going to do all these things. It's going to capture the photons at their optimal energies, at the optimal positions in space. It may be high performance. It's going to take this thing, which was a photonic bandgap device for a purpose, and this thing, which had an anti-reflection coating for a purpose, and this thing, which collected carriers with high efficiency, and it's going to be one thing that does them all taking advantage of the three-dimensional world in which we live, not the integrated just two-dimensional world, and it's going to be one thing that does it all.
And that may involve nanotechnology and
Oh, sure, because it's going to involve new three-dimensional
Right.
architectures that take advantage of the three-dimensionality of light and the three-dimensionality of morphologies. It could be arrays of rods that have different band gaps in them that are arranged with materials that have a different index. And so it actually does the spectrosplitting internally inside the material, and then the different indices that you've got from the different diameters of the rods, for instance, that are expanding in a porous medium to get the low index, but graded, then do the spectrosplitting, and it's done all by the three-dimensional architecture of the material that we impose as chemists and material scientists. And I think this is where it's going to go.
I mean, absolutely, the components are going to be far sub-wavelength. So we know the limits of sort of ray optics and geometrical optics, and we know we have to do much better than that. So inherently, there are going to be sub-visible wavelength and far sub-visible wavelength scale features.
Is there a question from our audience here in the room?
Thank you for, first of all, for beautiful talks. I think we've seen that photovoltaic or light trapping with photovoltaics has now gone to extreme high levels, and I was wondering whether there are similar opportunities already emerging, maybe in light trapping for water splitting, where I think it's less well defined what the optimum geometries and nanostructures are. Are there any thoughts on how light trapping in photocatalytic materials could be different or similar than in solar cells?
We know one difference. If you're going to do water splitting, you have to have water. So you have the optical properties of water to deal with, not just glass. You also have, if you're going to make oxygen as the water being the only large-scale credible electron donor, then you're going to have to deal with an index change when either you're making bubbles or you're at the vapor interface or some high-index, low-index material fundamental issue there that some people are worried about whether or not one could take advantage of refraction by bubbles, so directing light internally into the structures. Other people say you don't want them, you want to just nucleate them at the tips, but that means then you have how do you optically couple optimally the incident photons into the structure if it's also designed to, say, have a pointy tip to nucleate bubbles in a non-deleterious way from the internal volume. So the complexities, but the opportunities of understanding how to do the proper photon management and have the transport of reactants in and egress of products out in the solid-liquid interface is an opportunity that actually has not been explored very much.
Do we have another online question?
One of the people online who I think is a former undergrad with Nate, Andre, wants to know if any of these new technologies being developed by our EFRC will help the deployment of solar cell technologies to developing countries.
There's two extreme views on this as well, right? The one view is that the developing countries not having grids are primed to leapfrog the developed countries in terms of just like cell phone technology could be much more rapidly adopted there, and you won't be as price sensitive because if you don't have anything now, you know, anything to power your home at night compared to the one candle you have is a tremendous value added. The disparate view is if you can't meet the cost target for the nations that can afford to pay for energy, you certainly can't meet it for the ones that can't afford to pay for their energy. And so it will always come about first in the developed world. and then it'll migrate down to the developing countries. Probably the world is not black and white here, and there's truth to both of those extremes with, again, different coefficients that I'm not going to take a personal opinion on.
Microphone.
Paul, you said something that I thought was really interesting about suggesting that you think solar is going to be part of the big energy picture in the future, that maybe 15 or 10% is a really good sort of market share of the energy that we're using. Why do you say that? Why do you imagine a future where it's not all solar? Because I can kind of envision something where, you know, if you have every surface or just rocks passively generating electricity sort of ubiquitous in the environment, that seems like a no-brainer. That's better than mining or nuclear energy or whatever sort of other proposals that are out there. So what are you thinking about when you suggest that solar is only one fraction of the pie?
No, I'm a true believer in solar just like you, but there's a question of time scale. And, you know, I think, you know, we just have to recognize that energy is the largest industry in the world, and it takes time for it to change. And so if your time frame can stretch itself a century, then I have absolutely great confidence that solar will be, you know, the dominant source of our energy. But if you're trying to think about 20 or 25 years, then, you know, or hopefully even shorter, but, you know, achieving that 10% penetration would be terrific. And if you just look at the pace at which new energy technologies have actually gone from their initial discoveries to deployment that's quite widespread, it takes time to do that. And so we're in a particular time moment now, and we're watching solar at a very early stage, and it would be, I think that the German experiment where it's gone now to 15% over a 6-month period of electricity is a fascinating one, and one from which we're going to learn a lot. I think ultimately the solar, for it to go beyond that level, has to have a storage associated with it. It's obvious, right? And right now, the storage problem hasn't really even been demonstrated to have been solved. So, you know, that's going to take time, even from the point at which there's a demonstration to the point where it could become more widely deployed is going to take some time. That's not to say, I mean, from the science perspective, you know, we should be going flat out, trying to work on both aspects of these problems, how to make the electricity part better and more efficient and lower cost, and trying to demonstrate for the first time a really viable, scalable technology for solar storage, a la JCAP, or people's various ideas of other schemes for doing that.
I can add also, just keep in mind, even the carbon-based resources, we don't use exclusively one carbon-based. We have a portfolio of natural gas, coal, liquid fuels. And in the renewables, I think we're going to see the similar portfolio. Wind power tends to be the highest at night in the winter, and solar, of course, is the highest in the day in the summer. And so a balanced portfolio makes obvious sense even within the renewable space. And of course, in the long time frame, you know, these storage and other issues are things that will be overcome. But I think for the time being, a balanced approach pays the greatest dividends.
Emphasize that energy is not all about technology. In fact, it's arguably only at most a third, approximately, about technology. It's about policy and capital, and a changing landscape where 5 years ago, if somebody would have told you we would have had $2 gas, natural gas, they would have been laughed out. It was $10. And now with fracking, it's $2. It may be sustainable at $4. This has put tremendous price pressure on renewables that now are seeing a much cheaper prognosis for fossil-based electricity off natural gas that can be built cheaply, that will be able to fill demand, that doesn't have the downsides of coal-fired power plants. That now, if you look at the market perspectives for alternatives for electricity sources, utilities are dramatically rethinking whether or not they ever want to invest in the next 30 years at anything other than 5 cents a kilowatt hour from gas, because the price differential is now so much lower on the floor. This just means that it's great, and we need to think about all sorts of technology options, because we actually don't know what the energy future will be in 2050, because what we thought we knew 5 years ago is dramatically different from what it is now, which will be dramatically different yet again, I argue, 5 or 10 years from now. So we need to be working on the technology, but we can't just say, well, it's all solar, or it's all the above, or it's all nuclear. It takes a lot of time, and in the meantime, all these other geopolitical and social and economic forces change wildly.
I just wanted to, I totally agree with what Nate just said. He's right on. I just wanted to say one thing about, because people might have the impression that this natural gas change just happened from some, fluctuation of the universe or something. And because people here are working on problems that take decades to unfold, one thing I just think you should know, and you can look up about this, is that in the 1970s, when natural gas prices actually were quite low, the US started a research program, actually, partly at the behest of the industry, to try to develop the ability to extract oil and gas from unconventional sources, from shale rocks. And at various points in the time, especially when the prices fluctuated, you would find people saying, this is stupid research, stop doing it, it's never going to come to fruition, and so on. But the fracking that we have actually today had its origin from about 30 years of research in how to do horizontal drilling and trying to understand how those things work. And early demonstrations of those, much of it supported by DOE actually. And so, I agree totally with the statement that, there are going to be a lot of twists and turns in the energy space, but the fundamental research projects have a certain core to them that take time, and it's important to stay constant with them. Even in solar, there could be several twists and turns we don't anticipate right now over the next 15 or 20 years. And that's why, for example, I said earlier, I think it's really important for people working on organic solar cells, for example, to continue to do that, because we don't really know what the limits there are, and there could be discoveries that are a little unanticipated.
Okay, well, I'd like to thank our panelists for their participation, and all of our audience online and in person for your questions. And we welcome any additional comments. Feel free to log into our website, lmi.caltech.edu, and you can go to the Contact Us tab if you have any additional questions, and we'll try to get them answered. But we thank all of you for joining, and hopefully we can do this again, and we'll let you know. Thank you.